So LU factorization works most of the time. The places where LU factorization doesn't work is if we end up with a 0 in the pivot location. So if you remember, our row operations for LU factorization look like these, where we replace row 2 and row 3 using row 1, and then we replace row 3 using row 2. If there's a 0 that ends up there, then these row operations don't work, which means we need some sort of way to handle this. And the way we're going to handle this is using permutation matrices to do some row rearranging. So a permutation matrix is an elementary matrix that we obtain by rearranging some rows. So for example, if I rearrange rows 1 and row 2, my elementary matrix would look like this. So this here is a permutation matrix. And it turns out, if we multiply a permutation matrix by a matrix, it's going to go ahead and rearrange the rows or columns, depending on which side it's on. So if I do P times A, it would rearrange the rows. If I did A times P, it would rearrange the columns. And keep in mind that row operation, or that matrix multiplication, is not the same if your order is different. So AB is not BA. Same thing here. So if I do PA, it rearranges the rows. If I do AP, it rearranges the columns. It also turns out that the inverse of a permutation matrix is the same thing. So the inverse of a single permutation matrix, where we do one row operation, or one row swap, inverse of a double permutation matrix is if we did 2 row swaps. So if I swapped these 2 rows, so if they're all out of order, this here is a double permutation matrix, and the inverse is just the transpose of it. But the nice thing is those inverses are predictable. So the process of doing these permutations allows us to do PLU factorization, or PA equals LU factorization. You'll see it both ways. And this allows us to do what's called partial pivoting. So partial pivoting gives us a way to get around the fact that we might have zeros. And what this does is we're going to go ahead and put the largest magnitude entry in the pivot location prior to doing the elimination steps. So like I said, it overcomes this problem. We're also going to end up with the smallest values inside of L, which means we're going to have lots of fractions now in our L matrices. And we get an additional P matrix that's found during LU factorization as a result. But our steps are still the same algorithmically. So approaching PLU factorization ends like this. So first we get to REF by using these 5 row operations now. So first thing we're going to do is we're going to go ahead and put the largest magnitude value in the location 1, 1. So I want the largest value in my pivot location for column 1. So for example, over here, I have these 3 numbers in row 1. And the 7 is my largest in magnitude. So I would go ahead and swap these 2 rows. So now A is going to be 7, 1, 6, negative 3, 2, 7, and then 1, 4, 5. And so my matrix that does that is P1, looks like this. Same matrix, same identity, but my rows are swapped, same rows. So PA looks like that. And then I would do my row operations. So I would make this a 0 and I would make this a 0 using these same 2 steps like I did in LU factorization. Once I've done with column 1, then I move on to column 2. So then I would look at these numbers. I'm going to ignore everything in row 1 now, because I'm done with row 1. I'm not going to use it anymore. And now I want to go ahead and get the largest number in the 2, 2 location. So here I have to swap these. So P2 would look like this. So P2, P1, there's row operations in here. A equals whatever that would be. Then I can go ahead and make this one a 0 by using my row operation, my last row operation. And then I need to go ahead and I need to find P matrix, L matrix, and then whatever I resulted in is still going to be my U. So my U is whatever I get at the end, whatever REF is at the end of these 5 row operations. P is found by just multiplying my 2 matrices together. So multiply these 2 matrices together. That's pretty straightforward. L, though, is a little bit more challenging. L is a little bit more challenging. Essentially, what we're going to do is going to work our way backwards through these row operations and fill in L as we go, because now L needs to take into account the fact that we did these permutations. So what we're going to do first is we can go ahead and enter in L32 in the 3-2 position. And then we're going to apply our permutation matrix to that. Or we're going to apply our first permutation matrix. So we're going to do whatever we did here, we're going to do on our L. Then we're going to go ahead and insert these ones in our 3-1 and 2-1 locations, and then we can go ahead and do permutations on that one as well. So we need to work our way backwards. So it's not as straightforward as just plugging in our multipliers. We need to incorporate our permutations in L. And what happens when we do that, though, is L isn't going to be just a strict lower triangle matrix anymore. L might be rearranged. So we end up with the fact that PLU ends up being PA. And we'll see examples of how that plays out. There's also PDFs on UB Learns that play it out as well. Okay, but once we have our PLU factorization, then we can go ahead and plug it in to our system of equations and solve for our system. Same process or similar process as we did in LU factorization. So if PA equals PLU, then PAX equals PB. So I need to multiply, if I did my permutations on A, I need to go ahead and do my permutations on B as well. So when I plug that in, I get PLU X equals PB. And what happens is when we multiply PL times U, this ends up being a strict lower triangle matrix. That's why we keep track of P. So a lot of times you'll see just LU as a strict lower triangle matrix, but keep in mind that L, when we do partial pivoting involved, is multiplied by P if it's a strict lower triangle matrix. But then the same process applies as we did. We do forward substitution, back substitution. So PLY equals PB, where we solve for Y. Once we have Y, we can go ahead and plug that into the fact that UX equals Y and solve for X. And there we go. That is our approach for solving system equations using PLU factorization. So we're going to find our LU factorization, solve for Y, solve for X. And we'll see plenty of examples of these during class.